Hi, I'm Jacob Cherian, Chief Product Officer at Ioneer. Ioneer is a microservices-based, container-native storage and data management platform for Kubernetes. Today, I'm going to talk to you about name-based addressing of data within stored system and the unique capabilities that it can enable. As far as the agenda is concerned, we will look at how addressing works in stored systems today, introduce the concept of name-based addressing, the microservices-based architecture for the Ioneer platform that is enabled by name-based addressing, some of the unique capabilities that Ioneer has that is enabled by name-based addressing, and explore how these capabilities can be used to optimize DevOps workflows. To start, let's look at how data is addressed within stored systems today. Metadata is built around the concept of location-based addressing. Storage metadata maps between the logical location of a piece of data within a logical object and the location of that piece of data on a physical device. Location information eventually is an LBA on a block address device. So conceptually, a volume, or for that matter, any logical object that is presented by a stored system can be described in terms of the locations where the data for the volume resides. Now let's look at some of the challenges with location-based addressing. I will use the term volume going forward, but this could be any logical object that's presented by a storage system. The first issue that we have to deal with is portability. Location information is only valid within the scope of the system where the volume or the logical object is created and resides. Therefore, a definition that is based on location is not portable between systems. Another issue is that core metadata must be tailored for the performance profile and the profile of the data objects that we expect the stored system to typically handle. Lastly, what happens if the logical object or the media device is not block addressed? We need to translate between addressing schemes, and what about all the complicated data management functions that most systems support today? Now let's explore the idea of name-based addressing. With name-based addressing, metadata is built around the idea of named data blocks. When data is ingested into the system, each data block is assigned a unique name based on the content of the data block. The name can very simply be generated by taking a secure hash on the data block. Data can be chunked on ingest to support multiple chunk sizes to support different performance and data profiles. A logical object within the system can now be defined in terms of the names corresponding to its contents. This is addressing based on what the data is instead of where the data is stored. Name-based addressing brings a lot of benefits. First, because names are globally unique and the names are generated computationally based on the content of the data blocks, a volume definition that is based on names is portable. This is really important as infrastructure becomes increasingly distributed between private clouds, public clouds, and the edge. Data addressing independent of block addressing means that metadata is not tied to the properties of media devices or logical objects. In addition, with name-based addressing, when data is moved within the system, very often core metadata need not be updated at all. So how would the metadata look for a system that uses name-based addressing? Unlike traditional systems, where storage metadata maps between locations from logical to physical, with name-based addressing, metadata represents the relationship between the logical context associated with the data block and its name. So what is the logical context? In the case of block volumes, the context is the volume identifier and the LBA. The logical context is completely opaque to the system and is only used in retrieving data from the system on a read. Because the logical context is opaque, the metadata and therefore the system can be extended to support other types of storage frontends and other addressing schemes. Metadata in a system that uses name-based addressing is organized as a record of updates. Each entry consists of the time of the update, the logical context, and the name of the data block associated with the update. For a read operation, the metadata is queried with the logical context to return the name of the corresponding data block. Time information that is stored with every update allows retrieving of the state of the volume's data from any arbitrary point in the past. What about the data itself? Data needs to be persisted on media. Since data is addressed by name, what we need is a way to go from names and data to the actual storage media. This can be handled by a separate storage manager layer that is responsible for persisting data blocks redundantly. The redundancy scheme can be tailored for a given media type or for a given data profile. We also get automatic inline deduplication. The reason for this is that if the storage manager gets a data chunk to store with the same name as a data block that it already has, it knows it is a duplicate block and it does not need to store that data block again. Name-based addressing allows the storage platform to be disaggregated into microservices. The system consists of three main microservices: the front-end service, the metadata service, and the storage manager. The front-end microservice translates between the host side abstraction and addressing to a common language based on name, logical context, and data chunks. The logical context and the name is sent to the metadata service, while the data and name are sent to the storage manager to persist on media. There is one type of front-end service for each type of host abstraction or protocol that the system needs to support. The storage manager translates from name and data to the language required by a particular media device. The storage manager is also responsible for data redundancy. There is at least one type of storage manager for each type of media, and different storage managers can support different redundancy schemes. The metadata service receives logical context information from the front-end service during a write, adds time information of the operation, and inserts an entry into the metadata structures. The implementation of all data management functions are done in the metadata manager based on names and therefore are independent of location, host abstraction, and host and media. Therefore, the platform can be extended by adding new front-end microservice types and storage manager types without having to re-implement any of the data management functions. On a read, the front-end service sends the logical context to the metadata manager to get the associated name for the data block that it wants to fetch. This is then used to fetch the corresponding data from the storage manager. Multiple performance and data profiles can be supported since it's not limited by the metadata, but is based on the combination of front-end and storage managers. Data can be tiered between different types of media because looking into the system across all storage managers is based on name and data, and the system does not see the details of addressing or protocol of the individual media devices that it supports. Now, let's look at some of the unique capabilities that are enabled by name-based addressing. The first capability is instant mobility of data volumes between systems. Persistent volumes can be moved between Kubernetes clusters in less than a minute by relying on the fact that a volumes definition is based on names that are portable between systems. The process of mobility starts by moving a small amount of information about a volume between two instances of the system running on separate Kubernetes clusters. Once this information is received at the destination system, the volume is made available immediately to applications and is fully read-writable. Since the metadata is just a record of updates to the system, writes can be done at the destination site as a local operation without ever having to exchange any information with the source. This is at a time where there might be no data associated with that volume that has been fetched from the source cluster. For reads, multiple strategies are used. Since sending all the names corresponding to all the data in a volume can take a lot of time, a smaller set of names is initially sent. This set is constructed based on heuristics. The remaining names are read on demand or as a background process. For data, a combination of prefetch and data deduplication is used to reduce any impact of latency between sites or Kubernetes clusters in the same data center. Prefetch tries to predict what data will be required in the near future and prioritizes bringing in that data from the source. Names also allow duplicates between source and destination to be identified on the fly. The destination system drives the data transfer process, and if it already has a name locally, then it means that the data does not need to be fetched from the source. In addition to providing local access, this reduces the amount of data that needs to be transferred between two systems as part of the mobility operation. Data that is not identified using deduplication and is not brought in by a prefetch is read on demand if the data is requested. There's also a background process that brings in cold data. This background process is only applicable in migration and bursting use cases. In many DevOps use cases, where data sets may need to be made accessible for short periods of time, the background operation can be disabled to reduce network usage. Since instant mobility always sends a fixed amount of data between systems as part of the process to create a copy of the volume on the destination, the time the operation takes is independent of the size of a volume or the amount of data in the volume. The next capability is the ability to recover or clone volumes to an arbitrary point in the past. Since metadata stores the time for every update, recovery works by querying the metadata store with the desired time along with the logical context supplied by the application. Recovery is done by creating clones. The clones can also be used for rapidly creating copies of data. Each clone is fully independent and are first-class objects within the system. There is no difference between a parent and its clone volume. Today, the Ioneer container-native platform uses this technology to support recovery at the granularity of 1 second. Unlike log-based systems that are used for data recovery at fine granularity, it does not matter how old a copy of data is requested. The time to recreate the state of a volume from a second ago or 5 years in the past is exactly the same and takes less than a second. And there is no specific overhead associated with this capability. The clones are very efficient because they benefit from the deduplication that occurs across all data chunks in the storage manager. Now we will take a brief look at how container-native storage based on name-based addressing helps to eliminate data delays in DevOps pipelines. Today, IT is critical to enterprises as it allows them to gain insights on changing customer needs, identify opportunities, and deliver capabilities rapidly. Any acceleration to the speed at which code can be developed, tested, and delivered into production translates to a business advantage. DevOps infrastructure typically spans multiple Kubernetes clusters, and with the increasing distributed nature of enterprise IT, these clusters span across multiple clouds. There are multiple delays in DevOps environments as a result of data operations. These data delays may be in CI/CD and other DevOps pipelines that require datasets to be moved or copied within a cluster or between Kubernetes clusters. This may be to provide production datasets to development and test teams, or for test scaling, multiple copies of data may need to be provisioned rapidly. In addition, datasets may need to be reverted to reset operations or clear errors in test and development processes. Instant mobility and the ability to recover to an arbitrary point in time that is enabled by name-based metadata provides DevOps teams the perfect set of tools to eliminate the data delays in their pipelines. Now I want to take you through an example of DevOps acceleration using the capabilities that are enabled by name-based metadata. If you look at the pipeline on the top, the delays between the stages are due to data setup times. In the optimized pipeline, the 1 second time is for a data operation within a Kubernetes cluster using the ability to clone to an arbitrary point in time. And the 40 seconds represents an operation using instant mobility across Kubernetes cluster. Prior to the optimizations, Data delays amounted to many hours in the pipeline. After optimizations, data operations are completed within a few minutes in the pipeline. That concludes my talk on name-based metadata for storage and some of the unique capabilities enabled by name-based metadata. Thank you for your time. If you'd like to learn more, please reach out to me